Hello, and welcome to a video to revise your P1 topic, and this video is applicable to both combined and triple science students. Below is the areas that we're going to focus on today, and that is the ideas of systems, energy stores, and looking specifically at kinetic energy and gravitational potential energy. Now, these sections are highlighted green, as in the triple syllabus, these are the main areas of focus for the 2022 exams. However, it is still relevant to those of you who are studying for exams past that and on the combined syllabus. So let's start with what is a system. So a system is a group of objects that work together in order to complete a particular function. And energy transfers between systems via specific types of energy transfer. Now, these can be through radiation, through heating. It can be a mechanical transfer. Now, when we transfer energy from one system to another, it can also transfer from one store to another. And we're going to look at that in just a second. But there are three types of system that we need to learn about. And this is a bit of common content from your C2 syllabus on the higher paper, where we talk about equilibrium. On both papers actually, when we talk about equilibrium. So the first type of system we're going to look at is an open system. Now, an open system is one where both mass and energy can transfer in and out of your system. So if we say that the red arrow is our mass and the blue arrow is our energy. And the way I like to think about this, and it's quite a crude metaphor, but if I think of a cup that has no lid on it, okay? Again, really poor drawing, but I'm a science teacher and it kind of comes with the territory. So if I think about a lively hot cup of coffee that I've got here, this is an open system, and it's an open system because energy can transfer in and out. My hot coffee here with a very high thermal energy store, that thermal energy store is going to decrease as the heat energy is dissipated to thermal energy is dissipated to the surroundings. But equally, if I push my cup over, all of that can spill out. All of the mass that's within this cup can also spill out, and therefore this is an open system. The next system we can look at is a closed system. Now, a closed system, if I want to think of a model for it, I might think of like a bottle. Really poor drawing of a bottle incoming. Oh, that's poor. Very, very poor. With a lid on it. Now, this is because energy in a closed system can transfer in and out. That still happens. However, mass cannot. And so that's why the lid is a good representation here. Energy in this bottle can still transfer in and out. If I've got ice cold water in here, if I'm, we're in the middle of summer, eventually that water is going to warm up. Energy is going to transfer from the surroundings into the bottle, and that's going to cause that water to increase in temperature. Equally, if there were hot water in here, the opposite would happen. But because the lid's on there is no transfer of mass in and out of this system. Now, a closed system is what we talk about when we talk about dynamic equilibrium. So if when you do a reaction you put a bung in the top of your conical flask, that would be a closed system, and that means any gaseous products that you make would not be able to leave your reaction vessel. Now, the last type of system is an isolated system. And an isolated system is one where energy cannot transfer in and out of your system, and neither can mass. Now, a true isolated system is quite difficult to replicate because in order to make sure that no energy transfers in and out, in essence, you want to make sure there's a vacuum around this system, which means that there is no particles that are able to carry that heat, conduct that heat across. And the best sort of representation of this that I can think of in terms of something that you come across day to day is something like a thermos flask. And I can't draw a thermos flask, so I'm just going to write thermos on there, and that is lazy, but it's about as good as I can do. Now, a thermos flask is designed so that energy does not transfer in and out easily, and that mass also does not. Now, in reality, that thermos flask is not a true isolated system because some energy does transfer in and out. If we leave it long enough, it will cool down, but it is a good representation of what we've got. So let's think about the energy stores that we are actually having energy transferred in and out from. Now, for the purposes of your exams, we need to understand them as 8 energy stores. Now, previously, we've talked about them as energy forms, but actually, energy doesn't come in different forms, it's just stored in different ways. Pause the video now and have a go at thinking of these 8 yourselves. So, let's go through them one by one. So, the first one we're going to talk about, because it was in my metaphor just a minute ago, is a thermal energy store. And that is something that is hot. So, the hotter something is, the higher the thermal energy store is in that object. Thermal energy is also one of the most common forms of wasted energy. If energy is wasted from a system, it's normally going to be dissipated to the surroundings or transferred to the surroundings as a thermal energy store. The second one we can think of is chemical. Now, chemical energy is the energy stored between chemical bonds. And we can talk about chemical energy in terms of our food and fuel. Thirdly, let's think about kinetic energy. Now, kinetic energy is the energy stored within moving objects. Number 4, let's think about gravitational potential energy. And gravitational potential energy is the energy stored in an object that is raised above the ground. The higher the object is, the more gravitational potential energy it has. We can also include in here elastic energy, which is the energy stored in something that is stretched or squashed. And that's a potential energy. So when we pull an elastic band back and it's become stretched, there is more energy stored in the elastic store. When you release that elastic band, it will be converted into a kinetic energy store. Now, number 6, let's think about nuclear energy. And this is nuclear energy stored, not a nuclear energy resource, which is obviously something a little bit different that we're going to talk about later in this module. Nuclear energy is the energy stored within the nucleus of an atom, and we talk about it more when we talk about nuclear power, etc. Number 7, we can think about magnetic energy, the energy stored between different poles or like poles of a magnet. And lastly, electrostatic, which is similar to magnetic, but this time, rather than poles, north and south, we're talking about charges, positive and negative. Now, in your exam, previously, you will have been expected to memorise the equations for kinetic energy and for gravitational potential energy. You were always given the equation for elastic energy, and so these are the 3 that you tend to get more of your maths-based questions on. I'm going to focus on these 2 now, because these are the ones where you often get questions where they are combined to give you a higher level of complexity in your maths-based questions. So, let's talk firstly about kinetic energy. Now, yes, you are given the equation in the exam, but I think it's important that we do go over it just to make sure you're comfortable with it. So, kinetic energy is equal to a half multiplied by mass multiplied by velocity squared. Now, we can put that into a triangle. Now, I know that some of our maths teachers would probably prefer we weren't using triangles and practicing our rearranging skills, and that is absolutely fine. But if you find yourself getting towards the time of the exams and you're still not totally confident with rearranging equations, then we can absolutely use these triangles. So because we've got 3 things here multiplied together, we can put those at the bottom of our triangle. So we can put our half, but I'm going to write it as 0.5. It means the same thing, and it's easier to put into my calculator. I'm going to put my mass, and I'm going to put my velocity squared. At the top, I'm going to put my kinetic energy. Anything multiplied together, guys, will always go at the bottom of our triangle. Now, because you are given the equation, one of my assumptions is that perhaps we might be asked more about the units of these different quantities, and so let's quickly go through that. Kinetic energy is measured in joules, mass in kilograms, and velocity in meters per second. In physics, our mass has got to be in kilograms. When we do our chemistry and we look at moles, we're talking about it in grams, so please be mindful of that. Now, those are your kinetic energy equations. The thing I would just be mindful of here, just to remind you, just to warn you, I guess, is that this kinetic energy value, when you calculate it, will often be a very high number. Energy often is. And that's because of the unit that we're working it out in. That's absolutely fine. It's common to have answers in the tens of thousands for energy. That's why sometimes in the exam, they ask you to convert that into kilojoules, which gives you a more manageable number. But our base unit is joules, so we need to make sure that that's what we're using in the exam. The next one to focus on is gravitational potential energy. And this is a more simple equation because we haven't got the halves and the squares. So GPE is equal to mass times gravitational field strength times height. We could put that into a triangle again. And if you are confident in doing that, again, give this video a pause now and see if you can pop that in yourself. Now, as these three things along the bottom are multiplied together, we can put our mass, our gravitational field strength, and our height in the bottom. And we can put our GPE at the top. Now, when we talk about each of these things, we want to also talk about units. But before we talk about units, I just want to be clear about gravitational field strength here. Okay, this is the strength of gravity on a planet. And in the exam, they give it to you. Normally, they give it to you as 9.81. They can sometimes simplify that and just give it to you as 10. But they will give it in the exam, so just use what they give you. Now, the units for these, again, GPE's units are joules, mass in kilograms. The gravitational field strength is actually in meters per second squared, and the eagle-eyed of those of you will notice that is the those are the units for acceleration. And actually, this gravitational field strength is often referred to as acceleration due to gravity. And when you get to your A levels, then that will be the way in which you more commonly talk about it. And your height is in meters. So that's gravitational potential energy. Now, what I want to move on to now is to look at how we might use those equations together. Now, like I've said to you a few times, if you're taking your exams in 2022, then you will be very aware that you'll be given these two formulas in the exam. But what we need to be aware of is that that does mean that perhaps our calculations might be slightly more complex. They might want us to combine equations. And on the higher combined and triple papers, they often want you to combine these. And it's a nice way of getting 5 and 6 marks. So let's look at an example. Before I do go on to the example, though, let me just say that you can also be asked to combine the gravitational potential energy and elastic or kinetic and elastic energies. But it's the same idea, and I'll show you how to do that. So let's look at our worked example then. A ball of mass 52 kilograms was dropped from a height of 30 meters. What was the terminal velocity it reached? Gravitational field strength is 9.81. 5 marks. Now, if you feel confident at just having a go at this, maybe you've done some questions like this in your exam before, please do pause. And what I will say also is if you feel at any point during this explanation that you feel like you know where to go next, do pause and have a go and then come back to us at the end. It's really important that you test yourselves. So when you approach a question like this, my advice is always to write down what you've got or highlight those key numbers in the exam. So the first one I've got there is my mass. So I've got mass here of 52 kilograms. I've got a height of 30 and I got my gravitational field strength of 9.81. Now, that is a good place to start because now I can go and think, what equation do I have that has those three values in it? What can I work out? Because if you just try now and look for an equation to work out velocity, you'll realise that you don't have the values you need to work that out directly using the kinetic energy equation. So what you do have, though, is enough to work out gravitational potential energy. Apologies, put the pen on. So gravitational potential energy, as we've said, is mgh. Okay, and hopefully you remember in maths when you write them next to each other, that means multiplied by. So I do have my mass, my height, and my gravity. So I can multiply those together. So I've got 52 multiplied by 30 multiplied by 9.81. Popping that into your calculator will give you an answer of 15,303.6. And remember what I've said to you guys, that a really large number at this point is not something to be worried about. You do get very large values of energy. The units for that are joules. Now the next step is where we need to make an assumption. So as this ball is dropping, we need to make the assumption that the loss in gravitational potential energy is equal to the gain in kinetic energy. So as we drop it, the amount of energy being transferred to its kinetic energy store is equal to the amount being lost from its gravitational potential energy store. We'll talk about when that might not be the case in a second. So let's write this down. Now we can write that simply as saying is that GPE, or loss of GPE, is equal to gain in KE. Now, that's like saying, if I've got 15,303 joules of gravitational potential energy, then I'm going to have that exact amount of kinetic energy. And that means that we can rearrange our kinetic energy equation for velocity and use this number to help us. So, if we go back to our triangle over here to look at kinetic energy, I'm not trying to work out kinetic energy, I'm trying to work out velocity squared. So I'm going to cover this up and I'm left with kinetic energy divided by 0.5 multiplied by mass. So I'm going to go back down to my equation here and I'm going to write that out. Don't be afraid to write out as much working out as you need to. The examiners like to see it. So velocity squared is equal to kinetic energy all over 0.5 times mass, which for me is 15,303.6 divided by 0.5 times 52. And again, I could do that before and then pop that into my calculator. This gives me an answer of 588.6. And a common misconception here is to leave it there. But this is not your answer. This is velocity squared, not velocity. So our last step here to work out velocity is to do the square root of that number, which will give you an answer of 24.26. It's a velocity, so the units are meters per second. Meters per second, not meters per 8 even. Now, that answer is to 4 significant figures. Sometimes the examiner will say give your answer to 3 or to 2. Sometimes they even ask for it in standard form, which would be unlikely with a number this small, but it could happen. But be mindful that that's easy ways to get extra marks. So if your question says that, be sure to highlight that bit in the question so you can be clear. This is 5 marks, but it's really not difficult. It's a couple of equations you'll be given and a little bit of rearranging. And again, just a caveat, those of you who are doing your exams post or after 2022, you will have to memorise these equations instead. Now, like I said earlier, you could be asked this exact same style of question, but using elastic potential energy and kinetic energy, and it's the same idea. Work out the one that you are able to with the values that you're given, make that assumption, which will be the same assumption, and then use it for your next equation. So you've now revised that whole first section of P1. Go away and re-look at this if you need to, and come back when we'll look at specific heat capacity and internal energy.